All right, so we'll start for today. I'll introduce our speaker, Luke Strauss. Did I pronounce that right? I actually should have. Close enough. He is the engineering manager at Quality Bicycle Products. He's been there for about 5 years, had a series of positions before that. Before he entered industry, he got his master's degree at Cornell University and his bachelor's degree at Middlebury College in Vermont. So with that, I'll let Luke take it away and tell us about his work.
Yeah, welcome. Excited to be here. These sorts of things are a lot of fun since y'all are kind of at the beginning of a road, and you get to pick any door at this point. And it's hopefully something that maybe I can give you some windows of advice that from my old age of 12 years of experience, I wish somebody had told me 12 years ago. Real quick, I'm going to show the abstract, which you don't need to read, but it's on the video. So anybody else who's watching this and future people, that's what we're talking about. You've, I think, all already seen this. So with that, who am I? Why am I here? So as Devin mentioned, I got my undergrad at Middlebury. I did physics and philosophy, super engineering focused, right? Minored in math because math was fun. And then graduated from Middlebury, didn't really know what I was doing, moved to the mountains of Vermont and was a lumberjack for a year. And then to an engineering technician job where I worked for energy utilities, and then from there to civil engineering effectively, where I was doing pipelines and bridges and remediation and brownfield cleanup type stuff. That was a consulting engineering firm, which was super cool because they had one of like every single flavor of engineer available. And so I got to sit down and do info interviews with all those people and say like, wow, you're a chemie. What do you do? Oh, that's interesting. You spend your time with pipettes in a lab. I'd rather be outside. Oh, you're a civil engineer. You spend your time working on these regulations and working through and making sure that what we're doing is actually environmentally beneficial. That's super cool, but not really what I want to do. Oh, you're a mechanical engineer. You design things that don't exist yet. You try and solve mechanical problems. That's really interesting. Okay, I want to land there. And that's kind of how I ended up at Cornell with my mechanical engineering degree. And coming out of Cornell, I went to an automotive company called BorgWarner, which, if any of y'all are car people, you may be familiar with the name. I designed variable phasers for cam timing. So if you've seen like the Chrysler 300 driving around, I designed a part of that car, Subaru Outback. It's kind of fun to see your engineering DNA in the road. And then from there to QBP, which is, for me personally, the stuff I want to do, the stuff I'm interested in is 100% a dream job. I am an outdoors person, a dog, a kid. My 3-year-old has already been to the top of several mountains and rides pedal bike. I spend time in the Boundary Waters. I love doing those outdoor sorts of things, and as a result, working in an industry where I am talking with customers who love doing that sort of thing, talking with peers and coworkers who love doing that sort of thing, and thinking about it all day, and then leaving work and going and doing it on the stuff that I just got to design is really cool. So why does all that matter, right? I'm a dude. I've got some engineering stuff. Whatever. Like, I can talk about engineering. But a lot of what I'm going to talk about for the next 45 minutes is context. I have my own context. Everybody else comes from their own context. You have your own set of experiences, your own set of interests, and your own set of future desires. And those are totally unique to you. Folks who are in industrial design are trained in getting out of their own context. That's one of the things that industrial design focus on. Engineers, not so much. For industrial design, it's really important to be able to do that. For engineers, it is not as important as industrial design, but it is an important thing to keep in mind as you look at data, especially qualitative data. Quantitative data, you look at and it comes out with whatever the lab test was, and it's generally, if you do a test and you do a test and you both do the test well, you're going to get the same value if it's a quantitative test. But if I send a survey to the two of you, I'm going to get totally different results, and that doesn't mean that one of yours is invalid. So that context is really, really important. The context piece, you've all heard the term voice of the customer, I assume, probably about 10,000 times in the last 4 years. It's a super important concept. The voice of the customer, recognizing that that's what the customer wants, but recognize that even if you're trying to think about the voice of the customer, you're generally doing it through your own context. And that's a really important piece to keep in mind when you're looking at data and trying to make design decisions. There we go. So I want to start off with some words of wisdom and entertainment that, a lot of things that I wish I'd known. Kind of starting off, I didn't come up with any of these myself. They're all things that have been told to me at various points. The first is if something is worth doing, it's worth doing well. And if you're going to take notes and write anything down, the next 7 things would be it. The rest of it is just, my own advice. This is other people's advice, and they're smarter than me. But your reputation, especially as an engineer, and especially as you go on forward in your career, is your single greatest asset. And so if you're going to do something, if you're going to take it on, if you're going to do the project, it's worth doing well. And the converse of that, if you're not going to be able to do well at something, it's probably not worth doing. Manage your workload, take on what you can take on, and take pride in whatever it is you're doing. As a young engineer, you're probably going to get things that you are not the hardest project you've ever done. As your first year or two in engineering school, they may not be the hardest things you've ever done. They may not be the most challenging thing you can imagine for you. And you're used to school where you're constantly being challenged every single semester. Recognize that that's probably going to happen and that's okay, and that you still need to do your best work on those things. The number of young engineers that I've seen kind of fall on their face in the first year or two because their work isn't hard enough and they're ready for the next big thing, but they think they are, but they're not actually. Keep that in mind. Your reputation, especially in that first 6 months to a year, 2 years of a job, is what's going to carry you for the rest of that job. If it's worth doing, it's worth doing well. Deliver greatness every time. That's some of the best advice I've ever gotten. That's actually, deliver greatness is one of QBP's 5 guiding principles. That's where that particular phrase comes from. There we go. Second, if you can't explain how you're going to react based on the results of a test, it's not worth doing. If you're not going to do anything differently based on that test, why spend money and time and effort doing it? It's the number of times where you'll let's just do this test in a lab. Oh, cool. Well, are we making a decision based on that? Well, not really. So why should I spend 2 days analyzing data for this test that doesn't matter? That piece of, again, if it's worth doing, it's worth doing well. And that leads into this next one. I went too quickly. There we go. In God we trust, all others bring data. This is a pretty common one for engineers. I think is very frequently the same thing as I hope. And saying I hope this is true as an engineer or as a designer is not a great place to be. I hope this is safe. I hope this doesn't kill anybody. I hope this product works as intended. Strive to be able to say, I know. Bring data, get data, do the test. Strive. If the result of the test is you being able to go with confidence to the marketing team and say, this material that you're about to put out into the world and tell people what's going to happen is true, that's awesome. If it's confirming, the ability to say something out loud, that may well be important. That didn't work. There we go. Pants first, then shoes. Another way of saying this is pillage, then burn. Pillage and burn is terrible advice. Pillage, then burn. Order is super important. And if you do it in the other order, if any other orders, it doesn't work super well, right? If you burn the house down before you pillage it, you're just going to get a bunch of charcoal. Put your shoes on first, show up to class with no pants. I don't think anybody here made that mistake, which is awesome. Congratulations. that order in engineering stuff is really critical. If you get, if you run over the horse with the cart, you're going to be spending a lot of money making these really expensive, super highly machined, or maybe even tooled up prototypes, and you haven't done an FEA yet, and your first prototype breaks. You've just spent a lot of money and a lot of time, wasting money and time. Plan what you're going to do. Think about it. Think about what you need to do. Plan out the steps, then act. Any other order doesn't really work super well. Don't confuse activity with progress. It is really easy to be super busy. It's not quite as easy to make actual progress forward and take the data that you have and actually move the needle with that data. And in the design decisions, as you're making design decisions, make sure you're making design decisions that matter. Make sure that you're focusing your energy, your activity, in the right place, in a place that makes progress. That's something that, especially coming out of school, where you have electives that maybe you're not super interested in, and you have to do them in order to finish college, which is a very good thing to do. Those things, you kind of get into a little bit of a habit of some of the things you do are just kind of busy work. And it's always true that every job will have some amount of something that's not purely engineering. You'll need to log hours, or you'll need to, write this blog for this product launch. And it's not a strictly engineering task, but it's still something that needs doing. There's a reason for it. And make sure that everything you do, kind of like number 2, make sure that everything you do has a good reason behind it. Keep in mind that every single project is either finished or perfect. There comes a point where it's really just time to shoot the engineer and put the damn thing into production. And keep that in mind, so that you get to actually work on the next project as opposed to having your project manager just take you out back. But again, it kind of goes along with activity and progress and results of a test. When you're working on something and you're at the point where the customer probably doesn't care about the improvements you're making anymore. We worked on for a couple months on a surface inside of a pedal that we were designing, and then we realized that surface was covered up by a piece of the assembly, and nobody was ever going to see it, and so whether it was perfectly reflective or not really didn't matter. That activity with progress, making sure that you get to the finish line. Your paychecks for the rest of your life are going to be paid by the people who buy your stuff. And if stuff never goes on sale, your company is going to struggle. This last one is the most important. Leave a paper trail for yourself. When you collect data, when you analyze data, write it down. You're not going to remember what you did 2 years from now. Think about the classes you took, like sophomore or fall, and that lab experiment you did, and tell me why you made every decision you made in that lab right now. I'm willing to bet that most of you can't do that. And if it's 5 years ago or 7 years ago, for sure, tell me what you did in 8th grade. Tell me why you made that decision that you did in that, on Wednesday the 21st in 8th grade science class. Keep a paper trail. The only change in the last 12 years for this piece of advice is that I'm no longer surprised. The number of times in a given month that I go back into, things that I did at Haley and Aldrich 10 years ago. I remember working on this project. We did this experiment. What was the conclusion? Why did we conclude what we did? And bringing that data forward again. It happens probably at least monthly, if not more often. And then there's the questions, the less fun ones, where somebody says, hey, why didn't you get this done on time? And your response is, well, the scope has changed 7 times. No, it hasn't. It's been the same continuously. If you can say, nope, here's where you change the scope, here's where you change the scope, here's where you change the scope, understand, help people who are not technical understand just how big an impact the changes that they have been making over time actually make on the project. It'll help keep you and keep your work reputation stable. That isn't to say he said, she said type argument, but don't accept things that aren't yours, and that includes both credit and blame. Then I want to go into a couple of definitions just so we're on the same page about what I'm talking about when I use words like quantitative or qualitative data or context. First off, raise your hand if you think qualitative data is an oxymoron, or if you've ever made fun of somebody in the social sciences. I'll raise my hand. So half of you raised your hand, the other half of you are probably lying. It's a very common thing to do in engineering school to kind of to look down on the qualitative data. And that carries forward into the first couple of years of being an engineer in the real world. The faster you can get over that hump, the better. Qualitative data is super valuable, especially when you're making consumer products. That it's maybe a little less important how sharp the edge of the phaser is when the phaser is under a plastic cover, under a metal cover, under another metal cover, under a plastic cover, inside an engine. But it matters to the person who's assembling it. Does it feel sharp or not? But it doesn't really matter to the consumer. Most consumers don't even know what a phaser is. But paying attention to that qualitative data and recognizing that the context you bring to it is a lot of what's going to make it useful or not useful, and also really having genuine, deep respect for the people whose job it is to gather and understand and analyze qualitative data, and that's industrial design. Is anybody in here an industrial design major? Or are you all engineers? Cool. So industrial design is, if you have to pick the top two jobs, in my opinion, in the world, it would be those two careers, because the industrial designer is somebody who really understands what the thing is supposed to do in the world from the perspective of the person who's going to use it. And they're going to give you amazing feedback. I think you guys heard last week about kind of how those two goals are getting closer and closer as development times get faster and faster, and that's absolutely true. The industrial designer is a pretty amazing role, and a pretty amazing, having a good industrial designer as your partner on a design project is incredibly valuable. So quantitative data is not subject to debate, right? You go to a lab and you measure the weight of that ball. And if you hand that ball to somebody else and they go stick it on a scale, assuming the scale's calibrated correctly, they're going to get the same weight. Qualitative data comes from the person and is built into the context of the person who you're getting it from. That doesn't mean it's debatable. The other person's context is their context. So I might ask Devin, how do you feel about tractors? And you might be like, they're big and noisy. I'm like, I think tractors are awesome. That doesn't mean Devin's wrong. And that's a really important point to keep in mind when you're thinking about qualitative data. If all 10 of us from this room take a metal ball and go to the lab and weigh it, and we all find that it weighs 1 kilogram, and I hand it to one of you, and you put it on the scale in a funny way and maybe lean on the scale a little bit, and you get 1.2 kilograms, you're definitely wrong. Like, that's not reproducible. Quantitative data is kind of objectively provable and can be wrong. Qualitative data effectively never is wrong, because it's always coming from wherever you got it, in the context that you got it from. So I want to talk through a little bit of an example about qualitative versus quantitative data, just to make sure it's really, really clear. Let's pretend that you are a flower colorist, and your job is to make those super cool, really brightly colored flowers that you see in grocery stores that are where the flower petals are filled with dye. And to do that, you use a syringe with an injector, and you're trying to figure out whether this injector is the right injector for you. And so you go to the lab, and you measure the uncertainty, the flow rate, and the uncertainty in the flow rate based on the collection of injectors you've got in the lab. And you get a number, 1.2 milliliters per second plus or minus 0.01 to make something up, right? And you're like, cool, I have a number. These injectors will work. That's awesome. Now let's say your identical twin works in the medical industry, in some sort of medication device, and maybe they work in chemotherapy or psychoactive drugs like lithium. where the effective dose and the lethal dose are really, really close together. Your identical twin goes to the lab, buys syringes from the same supplier, and I need to understand whether or not this is a syringe that I can use. They go to the lab, they do the same thing, they measure it, they get 1.2 milliliters per second, plus or minus 0.01. Same number, right? The florist is saying, that's way too slow. And also, it's really accurate. Can I get it cheaper? Can I get less accuracy and get it cheaper? Right, they're adding their context to that quantitative data. The medical person is saying plus or minus 0.01, okay, that's really tight. I think if I control the medication this tightly, in solution, I think I can avoid killing patients, right? Totally different context, exactly the same qualitative data. Now let's say that you have two other people who both work at the syringe making company, for this example. And one of them is tasked with understanding what the needs of your customers are. And they send a whole bunch of surveys out to flower colorists. They're going to get answers back on the survey of what's important to you, like, can I get them in bulk? Is it possible to maybe sacrifice some accuracy and make them less expensive because I go through these things by the hundreds every day? Is there a way to make them assemble faster so that I can do more flowers more quickly? That researcher, that industrial design researcher, is going to come back to the team with the context of the people they talk to and say, here's what the customer needs. Their partner sends out a whole bunch of questionnaires and sends them to the medical side. And they're going to get things like, can you make it more precise? I don't care how expensive it is. Can you make it sharper? Can I get it in single packs because I only use one syringe for one person every 2 weeks for treatment, and the 10-pack, what do I do with the other 9? Totally different context. The qualitative data that comes back in that research, if you only listen to one of those two points of view, then you're going to be operating in that context. And so keeping in mind the context of the qualitative data that's coming in, we were working on a cargo bike, and we talked with a whole bunch of people who are cargo enthusiasts, already own a cargo bike, and live in Seattle. And that was our data set. Those were the people we could find to talk with. That's pretty narrow context. Also, the people who already own a cargo bike generally aren't the people who are about to buy one from us, because they already own one. Bikes, the lifetime of a bike in the field is generally about 10 or 12 years. So if somebody just bought a cargo bike last year for $5,000, they're probably not buying another one this year. So great context from the perspective of why did you decide to buy one? Not so great context is like what would convince you to buy ours. So again, qualitative and quantitative data, a lot of it comes down to the context. And the context is essentially the set of experiences, the lens that you're viewing a piece of data through. Cool. Let's talk a little bit about context failures. Who remembers the Nike Fuel Band from 5 years ago? So this is a quote from a news article about how they failed. They sent their Nike Fuel Band to a bunch of people who were super technical and were given the product for free, and they were asked to describe the experience. And the reviewers said, this is an amazing product. This thing is so cool. I love it. I wear it every day. Well, of course you wear it every day. You got it for free, and you're supposed to be wearing it, right? And then they put it on the market, and nobody bought it. And 10% market penetration after whatever it was, 2 years, that's pretty terrible for a first-to-market device that is supposed to, 10% is not over the adoption curve. That's early adopters only. Have y'all seen the Michael Sintek Why TED Talk? It's a pretty common one in a lot of engineering classes. It's called, look up Michael Sintek Why, Getting to Why, and if your market penetration is 5, 6, 7, 10%, like that's great. You have some early adopters who will buy any technology because it's cool technology. You do not have market penetration, and that's so 2 years after its release. Nike not only killed the product, they also had fired most of the team. because that team had sat on some pretty poor context and really kind of ignored data as it was coming in those first 2 years, and shot themselves in the foot. Talk about another one. Who remembers the Galaxy Note 7? This is an example of when you ignore quantitative data. The Nike Fuel Band is ignoring qualitative data or not paying attention to the context of the qualitative data. This one, Samsung had battery fires in testing before they released the Note 7. They knew that there was a possibility of this sort of thing happening. And for whatever reason, I wasn't at Samsung, I don't know the story, but they decided to go to market anyway. And they resulted in a hotly anticipated product where hotly was maybe ironic. I think that it was on the market for 2 months, if I remember correctly, before the recall started, and I believe the last one was off the streets like 3 or 4 months later. That's a really expensive failure. If you think about how much tooling and supply chain ramp up goes into launching a flagship phone, that was a really expensive mistake. And again, it came from ignoring quantitative data that was available to them prior to launch. Second definition, phase gate process. Y'all come across this in any class yet? So you've all heard about the development process, right? So I want you all to take out your phones or your laptops and jump onto Google and look up phase gate process and go to the image tab. And you can also check your text messages real quick while you're at it. Just scroll for a little bit. Look at how many of them there are. It's pretty crazy. Phase gate process. Phase gate process for product development, for software development, for you name it, engineering thing. As you scroll through, there's a lot of them. Every single one of those is somebody's proprietary phase gate process. You can put your phones back down now. Some people call it the proprietary development process. Some people call it the PDP because they really like TLAs. That's a 3-letter acronym for those who aren't familiar with the TLA one. Some people call it the Toyota development system, right? That one's, clearly Toyota's, right? Some people call it the way we do development around here. We're right. Everybody uses a phase gate program. A phase is a period of time where you do some stuff, and a gate is a point in time or a point in a project that you have to have some certain things done. And good example of that. Think about going to the airport to fly on a plane. You can buy your coffee before you get to the airport, maybe before you go through security, maybe after you go through security, maybe you can get it from the flight attendant once you're on the plane. It doesn't really matter where you get the coffee. But you better have your boarding pass before you try and go through security. Right? Security is a gate. You have to have your boarding pass, your ID. You can't have certain things like a knife in your pocket to get through security. So there are certain requirements to passing through that gate, and there are certain things you have to do beforehand, like getting your boarding pass, and there are certain things that can happen either before or after, like getting your coffee. And if you forget your wallet, and it's on the other side of security, you have to go back through, and you need to go get it. You have to go back through security again to get to the plane side of the airport. So gates, you can't go around a gate, generally speaking. And pretty much every single company in the world uses a phase gate process. They're all going to call it something different. They're all going to have little nuances. That's ours. There's a bunch of phases, and the lines are the gates. We have a phase gate process. Hooray. We happen to call ours PDP, the product development process. QBP is a company that very much likes TLAs for the record. So that's our phase gate process. And this is really nice and linear, and it's really clean, and it's super clear exactly where you are. But the reality is that every single phase is really an iteration. And you're doing a design phase. You make a design, you do some prototype, you do some evaluation. You ask whether it's meeting the needs of the marketplace, of the user. You ask if it's passing testing. You ask if it's, all of these questions, and you change it. And then you get some information from some field testing, and it changes what you think the product should be, and then you might change it a little bit. And there's a lot of little decisions that get made in these iterative processes. So the reality is that it's a lot more messy than this, super clean, nice straight line. So how many of you guys like Dilbert? This is one of my favorites. Feature sets get rather rich sometimes, and sometimes they get a little bit complex. So let's talk a little bit about how the complexity really happens, right? This is funny, and if you look back at this in like 5 years, it'll be way funnier because it will have actually happened to you like 10 times. And Dilbert is one of those that definitely gets funnier the more experience you gather. So let's do a quick exercise. So I've only got one, but imagine this is like 10 sheets of paper. I was going to tear them off the pad, but I want to hold these together. What's the way to do that? Staple. Okay, so so there's two. What's another way? Fold them together, right? He said staple. Are you wrong? No, right? There's lots of right ways to do something. There's a staple, there's a paper clip, there's a rubber band, there's fold them together, there's super glue, right? There are a lot of examples to how you can solve a problem. And maybe folding them together is the right answer because you need them to fit in this envelope. I'm sending a letter to somebody. Stapling a bunch of whole pieces of paper and then crumpling it up to shove it in the envelope isn't going to work super well, right? Maybe I need to make handouts for a class. Folding them up is a really good way to make sure that the pile of them falls on the floor and they get mixed up. Staple makes a lot more sense, right? So there's those little considerations in the class handout. A staple makes sense. A paper clip makes sense. A rubber band makes sense. Maybe setting the pages out individually and having people take one page each, if it's like a 3-page handout, makes sense. In the envelope example, maybe it's get a bigger envelope and keep it flat. Maybe it's roll it up and put it in an envelope roll with a rubber band. Right? Rubber band might have worked for both. So there's these design decisions where there isn't an obvious right answer. How do you hold these pieces of paper together is a really super simple example. Scale that up to like a bike or a car or a wind turbine. What's the right way? Wind turbine. Sitting in wind. Wind is not exactly a constant thing. You have like 1,600 tons of blade spinning around with a lot of rotational inertia. The tips of for those if you haven't studied wind turbines at all, the tip of a wind turbine, the blade tip is usually moving pretty close to the speed of sound. It's generally moving about as fast as a 747 flies. 500-600 miles an hour. That's a lot of mass moving really fast. And all of a sudden the wind stops blowing. And now instead of this giant set of blades turning a transmission to make power, now the transmission is turning the blades. And so you have this tremendous reversing torque problem through the transmission, where if you have any lash in your gears, they're all of a sudden smashing back and forth into each other. And it's if you've seen videos of like wind turbine nacelles exploding, it's usually the transmission that's failing in those videos, and it's a lot of times because of the reversing torque problem. How do you solve that problem? Well, there's like 7 major wind turbine companies in the world, and every single one of them has a different answer to that question. And every single one of them installs wind turbines, and for the most part, all of their wind turbines work. So a really good example of real business application where there is not one right answer. Another way of saying that, like, how many products exist in the world? How many of them are perfect? Right? If it was easy and obvious to pick the right answer for a product, none of us would have jobs. So let's talk about finding a design solution. I'm going to talk through these 3 things: the types of testing you might do, making design decisions, and then living in the gray, which is where I'll close here. There we go. So as a product matures, you have a bunch of different ways to test it. You can do simulation, FEA analysis, you can do pencil and paper work, you can calculate things. That's really easy to do. The investment to do it is really cheap. Basically, you need like yourself and maybe a computer. Then you have lab testing. And lab testing is great. It's super controllable. It's less cheap because you have to get something to test and you have to get the equipment to do the testing with. It's not as fast because you actually have to do some testing, and maybe that means like waiting for an ozone machine to do a 30-hour aging test, right? Do a 30-hour aging test in 10 hours, go. Good luck, right? Run an FEA. I need it done faster, cool, get a faster computer. So there's some scale that happens between those two. FEA, if you run an FEA and you're like plus or minus 20% from reality, that's a really good FEA. If you run a lab test and you're like plus or minus 20% standard deviation compared to your data, that's not so good. So FEAs will give you a great kind of thumb in the wind idea of where things are going. Back of the envelope calculations with some super consistent, totally isotropic material that has a very precisely known modulus. Right? If you get 20 samples of steel, even from the same batch, and you cut them all into coupons and you test all of them, they are not all going to have the same modulus. So when you do this really nice calculation that says my bridge is exactly strong enough to hold 4 pounds and it will break at 4.01 pounds, and I'm going to use that steel, that's a real small safety margin. And you're probably not going to be able to do it. You can calculate it just fine. You can say my factor of safety is 1.2, 1.5, 1.7, 2.0, 2.3. Those are great. But if you're like 1.01, you better be doing 100% testing because stuff does vary in manufacturing. And then there's field testing, which is really expensive and really slow. You have to not only get a product which is good enough that you're comfortable sending out in the field, which means you've done all the other stuff first. You also have to pay for generally pretty expensive things. And you also have to send it to somebody and then wait for them to bring their context and bring their data back to you. That said, field testing is really the only way to get qualitative data about a product. Whether or not you are going out into the field and testing it yourself, or you're sending it to somebody else and testing it, the feedback that you get from that is really the only way to get solid, real-world qualitative data out of a product. You can't show a bike frame to a bunch of mice and see whether they run to the left side or the right side of the room and decide whether the bike frame looks good. Cool, I didn't miss anything. So let's talk a little bit about intentional misuse. So when you do field testing, you're going to get, generally speaking, you're going to get feedback about the product being used the way it was supposed to be used. And often you're going to be surprised by the data that comes back. Salsa bear grease is a great example of that. We went into the salsa bear grease, which launched in 2016, if you're not familiar with it. It was the first of its kind, race-ready, race-specific winter fat bike. And we looked at that, and internally we did a bunch of field testing, essentially, context building inside the building, and said, yeah, racks are really inappropriate. Bike racks are really inappropriate for the type of racing we're designing this bike for. We designed the bike with no holes for mounting a rack to it. And then we kept going. We finally got our first off tool. So this is a $40,000 carbon tool that we've now made. We got a bunch of them. They shipped to here from Taiwan. They were on a boat in the ocean for 3 months. So we're, $100,000 in the hole and 6 months of just waiting for these prototypes to be manufactured and then shipped to us. And then we stick it in a box. It's in shipment with UPS for another week, and it goes to one of our sponsored racers. He uses it. He's thrilled with it. He loves it. He sends us a bunch of pictures, and there's a rear rack on it. He had drilled some holes himself into the chainstays and put little threaded inserts in there so he could mount a rack. Obviously intentional, right? Obviously misuse. It's not what we intended. We didn't put holes for a rack on it. But we took that and we're like, oh man, Jay is like a legend among endurance racers. Like he's won the Iditarod bike 1,000-mile race like 5 years in a row. People like he speaks all over the country about racing. He probably knows what he's talking about. Like if he thinks that we really need to be able to put a rack on this bike, we probably really need to be able to put a rack on this bike. And taking in that, being open-eyed, and you have three choices when you get this kind of surprising intentional misuse for it. You can accept that fact, which is what I was just talking about. You can reject it. You can be like, nope, Jay's an idiot. That's not what we're supposed to do. It's not how we designed it for. We need to put some metal cladding on the chainstays so that you can't drill a hole there because it's just not. That's not how it's supposed to be used. Or you can just ignore it. You can be like, well, Jay's just one dude. Everybody else will use it, right? You have those three choices, and I say it a little bit in this particular example. It's kind of obvious which one we picked, right? We ended up designing what's called the Salsa Rack Lock, which is a seat collar that allows the use of a rack. And the next generation of 2017 Bear Grease, we put holes for rack mounting on. So we did change the direction of the project after all of that, tooling investment, everything else. We changed the spec in the first year, we changed the actual physical product in the second year because of that intentional misuse from field testing. And then there's the other kind, unintentional misuse. This is the sort of stuff that keeps especially product safety people up at night. Sometimes you'll send your product out into the field, and people will see a feature that you intended to be used one way, and they think they're using it the right way, and they're using it not the right way. Let's talk about the Cutthroat Carbon Fork. This is a product that we released with the Cutthroat, which was endurance racing mountain bike. We released, the first Cutthroat came out, I think, in 2017. And we made an update to it last year. We released the Cutthroat Carbon Fork, and it's called the Fire Starter. And it was a super cool fork because it had internal routing for a dyno hub, for a generator hub. So on these really long, like 12, 14-day races where you're riding like 250 miles on mountain bike trails every day, the racers ride through the night, and you cannot carry enough batteries to light your way. So most of the riders use what's called dyno hub, which is basically just a little generator. It's like usually pulls 5 watts of your forward energy and sends it somewhere else to a light or charging a Garmin or something like that. And we put in dyno cable routing inside the fork. So instead of having to tape this wire and have it flapping out and catch on a cactus and then to replace the wire, you could run it inside the fork. And there was a hole at the top of the fork to run the wire out so you could run it to your headlight because electrons like to stay in wires that don't generally jump gaps super well. And cool, awesome product feature. We had a blog about it. We had it was in the instructions. Here's how you route the cable through it. It needs to run this direction, not that direction, because if you run it the other way, it's hard to solder or hard to attach. Here's the types of leads it accepts. Here's the biggest gauge wire you can run into here. Here's the highest amperage. We had all this stuff about how cool this new feature was. And most people used it the way we intended it. They ran a dyno cable through it. And then we started getting warranties back after we launched this product. And a lot of these holes were ripped out. It looked like they'd been ripped out by a bolt. And we started digging into this. And we found that a lot of people were assuming that this was a single point mounting point for a front rack. And they were shoving a bolt into this threaded hole that was not supposed to have a rack load on it. And they were also using single point racks, which if you imagine a very large heavy object right over the front wheel of a bike with a bunch of sticky outy things that can go into the spokes, mounting it with only one point of failure is generally not a very good idea. But there are companies out there that make single point mounting racks. And people were putting them on our bikes. And that, of course, is minorly panic-inducing for the people who are responsible for making sure we don't get sued out of existence. And again, you have 3 choices. You can accept it. You can say, well, people are going to use single bolt racks whether we like it or not, so we might as well just make that bolt hole stronger. Might as well make it as strong as we can because people are going to use it that way. And in a lot of cases of unintentional misuse, that is exactly what happens, right? How many cars have airbags today? how many people intend to crash their cars. With that safety, they don't say, well, people should just not crash their cars. They put in a safety feature. So that's the acceptance path on there. You can reject it. You can say, you know what, we can be as idiot-proof as we want. The universe will just always invent a bigger idiot. Tough. Some people are just gonna use it wrong. We can warn them, but like, an idiot's an idiot. It's just how it works, right? You can also just ignore it. You can be like, well, it's rare. Let's just not worry about it. It's only a few people. We've only gotten 3 forks back that look like this, and we've sold like 10,000. 0.3% or 0.03%. It's not a big deal. All of those are options. All of those have happened. All of those are decisions that get made, and none of them are wrong. I say it kind of tongue in cheek with this particular example because I know what we did. I know the answer that we chose. But car example, you react to the fact that somebody might unintentionally crash their car by building a stronger safety feature. You react to the fact that some people might hit a rock on a mountain bike trail and go over the front of their bars by accepting that that's going to happen sometimes. You can't control how somebody rides and make a product that is a bicycle. And sometimes, in the case of this particular product, we rejected that. We put a sticker over that hole that said this hole is for cable routing only. We changed the paint job of the actual fork so that there was a light symbol right next to the hole and a rack with a line through it, so that even if you took the sticker off, there was a sign to the user that said, this is not for racks. And we also added a bunch to our instructions and released a safety notice saying, like, this is what this hole is for, don't use it for anything else.
Even after that, did you still get some people that tried using it?
You do, yes, absolutely. You have people who look at that and be like, I'm a better engineer than the people who engineered this product. I'm going to do it anyway. You absolutely do get that. But the difference is that when you have really, really clear warning and somebody explicitly violates your warning, it's on them. And you can't prevent people from doing whatever they want to do, right? They have freedom of choice. They can take your bike fork and they can make a sculpture out of it. That was definitely not an intended use. So yes, you absolutely do get that sort of thing. And your goal as a product designer is to make the thing as safe as possible and make sure that the user has enough information that if they are using it incorrectly in a way that in an intentional misuse that you need to reject, that they know that they're doing it, so that they are not, putting in the first generation, they put a rack on there. They had no idea, really. It was buried in the instructions, but how many of you guys actually read the instructions on bike part? Right? Nobody raised your hand, and I'm not even a little bit surprised. You have it in the instructions. This is a light routing. Here's how to use it. Somebody pulls it out, tosses the instructions in the trash, throws the fork on their bike, and or they go to the bike shop and they buy a fully built bike already assembled, and it's got a little wire with all of the instructions in a little bag hanging on the handlebar, and they drop that in the trash on their way out of the bike shop. And then they get home and they're like, I really want to put a front rack on this. And they do, because there's a hole there for it. And they can go to the same bike shop where they bought the bike and buy a rack that has a single mounting point. And this particular fork actually has a 6-pack rack mounting on the fork blades designed to take 4- and 6-point racks and accessories on the fork. It's even designed with the ability to hold racks, just not that kind of rack. And still, people were making that mistake, and they didn't. If you were the user and you went to put the bolt hole into that light hole, and you saw a little symbol that said no racks, you might say, oh, I should probably return this and get a different kind of rack. Or you might say, nah, I don't care. The designers are stupid. Salsa doesn't know what they're talking about. It's in the right place for a rack. I'm just going to use it that way. That absolutely happens. Design decisions. And, are you designing for, yeah, I'm two slides out. We're right on time. I was just glancing at that actually. Are you making decisions for performance or safety or compliance? You might have and this is a plot that I deliberately took the actual numbers and scale and units off of and the title off of, so it's just like a data plot as opposed to an actually good engineering plot that you could understand anything of, because that could be a picture. It could just be like my kid's splatter painting. But are you designing for performance? Is this something that is a decision about how you want something to work? It's not necessarily safer or less safe. It's not necessarily legal or illegal. It's a question about, I'm designing a bike. Do I want this bike to be really stable at high speeds like a gravel bike? Or do I want it to be super quick steering like a criterium bike? It's a design decision. Do I want the person riding this to be encouraged into a really upright, comfortable, like cruiser-like posture? Or do I want them to be, down in a drop and in a really, aerodynamic, super highly energy efficient posture? Those are performance decisions, and they're ones that industrial design will help guide kind of what the user wants, and then the engineer's job is to make sure that the product actually does what the user wants it to do. And also, in a lot of cases, figure out the numerical qualification value. The user wants this back end to feel stiff. That's nice. I'm going to go do a lab test and put feel stiff into the MTS machine. Right? That's the engineer's job. What does feel stiff mean? And what's the acceptable tolerance? And what's the limit criteria? And how important is that performance to the product? Is that something we need to test in batch in production? Those are all engineering decisions, and they're all based on the industrial design feedback of here's what we're trying to do. Here's what this thing should be. And then you have safety decisions. Safety decisions are probably your greatest responsibility. All of you are going to go out into the world and design things that absolutely can hurt people. It is 100% impossible to design a product that cannot be used to hurt somebody, either the user or somebody else. If any of you can name one, I will pay your college tuition. Right? That's how confident I am in that statement. It can't be done. And your job as an engineer is to make it acceptably safe. The level of risk of a failure in an airplane, for example, a sensor that tells whether you're going into a stall, to use a current event, the risk associated with that failure is like 300 people's lives. And Boeing screwed that one up really badly. They failed to do it from the outside. It looks like they basically failed to do a DFEMA on a brand new system. Classic overfunction of a sensor. What happens if it overfunctions? This system does it, and the pilot can't correct for it, and the plane goes nose first at high speed to the ground. Right? That's a safety. That's safety you'd really need to pay a lot of attention to. There's a lot of risk there. The edge profile of printed printer paper. It is possible to get a paper cut from printer paper, but I don't think they probably spend a lot of time doing 100% inspection of every single piece of paper in a ream of paper to make sure that the edge condition is not so sharp that it can't cut somebody. Right? The safety engineer, the engineer at the paper company and the company that is making that paper does not believe that the risk of a paper cut to their consumer is a risk that is worth the cost of doing 100% edge profile inspection of every single piece of paper they put into a package. It's a good bet that going forward, Boeing will be doing a very careful inspection of every single sensor on a plane, probably much more so than they had been doing prior, when they assumed that these sensors were going to be good. And then the last is compliance. There is a whole network of really complicated laws out there, and the laws do not generally keep up with the speed of product development. And a lot of times you get into these kind of funny situations where what the law says is applied to this other thing that didn't exist when the law was written, and the way that the law reads is kind of funny, but you got to do that test anyway. And if you want to be able to sell it, if you want it to be legal, you need it to comply, and those are compliance decisions. Just real quick, I want to go through a couple of examples of that. Terravel Cannonball, designed as a tire for gravel, and that's we're trying to design a tire that's amazing. Gravel, especially in like Kansas, is made out of flint, which is the same stuff that early Americans made arrowheads out of, and it's not particularly nice to tires. So you need to have something that's really, really puncture resistant, really cut resistant. Puncture resistance, cut resistance make a tire heavy and stiff, and those are not things that generally make them feel good when you're riding on them. So you have a choice when you're talking about a performance decision. You can optimize for one thing. You can say, this tire is for riding on gravel. It's a dirty Kansas tire. It's going to be puncture resistant. I don't care how heavy it is. A heavy tire is always faster than a flat tire. Or you can say, let's compromise. It's going to be used for DK. It's also going to be used for all these other things. It's all right if some of the users get flat tires. It also needs to feel comfortable on pavement. There's no right answer to that. I want to stress that. There's really, all of this stuff that I'm talking about, there is no right answer. And in this particular one, we optimized for the best possible gravel tire, and it still is the best gravel tire on the market. It's really not particularly pleasant to ride on pavement, and it sucks a lot in mud, but it's great on gravel. Safety versus compliance. There is a set of laws that were applied for bedding materials, written in like the early 1800s, when tents were made of canvas, and people had house fires fairly frequently, and they would fall asleep with cigarettes, and people dying in their beds because of fire was actually a pretty big issue. There's a set of laws that was written, and now that we've moved to like really lightweight nylon tents, that law is still in the books, and so every single tent that gets sold, if you go inside the tent, you'll find a little tag that says, like, this thing is treated with fire retardant, but it can still burn, ... And the reality is the fire retardant on a bunch of nylon doesn't do anything. It has to be there because the law says it has to be there. It does not make a user safer. It might actually make them less safe because they think that maybe they can get away with using their stove inside that tent. But if any of you have ever seen nylon burn, you do not want to be wrapped up inside of a giant nylon bubble that is now on fire. Even if you haven't been in, haven't seen nylon burn, you can imagine that that's a really unpleasant place to be. So, what do you do, right? You can you can make choices around that, where you have to comply with this law if you want to sell the product. You also want to make the product safe, and that's why there's a warning in there saying, like, yeah, this stuff has flame retardant on it, but it doesn't do anything, so don't burn it. That tag really ought to just say, don't burn this tent. Like, keep flame away from me. But at the same time, you're making these decisions, which those flame retardants actually have some pretty terrible environmental effects. And people who buy really nice tents generally also care about the environment, because most of the time they want to use that tent like out in nature somewhere. That's kind of what camping does. And so you're as a designer of a tent, you're making this really tough decision about what flame retardant do I use. I have to comply. I have to make the product safe. I have to add this tag, which adds weight, and people don't like weight, and so they're going to rip it off, and then they're not going to know. But at the same time, you want to be sensitive to the first dozen times that tent goes in the rain, it's going to put toxins into the rainwater because of the flame retardants. And then lastly here, living in the gray. I want to leave you with that. You can't possibly do every single FEA simulation. You cannot possibly do every single hand calculation. You can't do every lab test. Going back to where we started, don't confuse activity with progress. Do a test that's worth doing. Make sure that you're picking things that matter, and rely on your design teams to give you that information. And your own judgment, when turns to talk about safety. If your gut says this is unsafe, probably is. That's it. Thank you.